Do you know what's worth fighting for when it's not worth dying for? Does it take your breath away and you feel yourself suffocating? Does the pain weigh up the pride and you look for a place to hide? Did someone break your heart inside? You're in ruins. 121 guns, lay down your arms, give up the fight. 121 guns, throw up your arms into the sky. You and I. When you're at the end of the road.
Right, I promised to give you a lecture on LIGO. So here we go. I'm doing this off the cuff. I haven't prepared it, I'm just going with what I know. So in 5 minutes I'm going to try and tell you about LIGO. So I've got my arms out. You can see my arms are at 90 degrees to each other. So they're like arms and they're orthogonally connected. They are the same 90 degrees.
GPS signal lost.
Now LIGO is just like that. It's two arms that are 2 kilometers long. Well, they're actually longer than 2 kilometers. What is important is the component parts inside the arms are 2 kilometers apart. And the important part of the arms are 2 mirrors. And the mirrors weigh, pardon me, the mirrors weigh 44 kilograms each. And they are suspended on very thin but very strong wires. So they're just hanging vertically. Now the whole point of LIGO is to intercept gravitational waves. Now gravitational waves were a consequence of Einstein's general theory of relativity, which he created in 1915. He wrote a paper in 1916 where he posited gravitational waves. He thought gravitational waves would never be seen by anybody, that they would be too weak to ever be seen. When Einstein said this, lasers did not exist. Laser technology has been going for 30, 40 years. It's advanced a lot. Other things were not so clear. The quantum mechanics was not well developed in 1916 when Einstein thought that we wouldn't discover gravity waves. The quantum mechanics was not well understood and not even really formed. Einstein played a part in the development of quantum mechanics with his wave-particle duality of the photon. Einstein came up with the photon, and we know that a photon has wave properties and it has particle properties. It is a massless particle. As a massless particle, it travels at the speed of light. In fact, a photon is light. What we call light is a photon. Photons carry electromagnetic radiation. Part of the spectrum of electromagnetic radiation is the visible spectrum, and those are the photons that we're familiar with. These photons give us the perception of light, the perception of everything. We see by photons entering our eyes and hitting our the nerves, our optic nerves. We have rods and cones. The cones perceive colour, the rods are black and white, on off. People who are colourblind have one of their cones is not so good. So green and red to someone who's colourblind appear to be the same. Someone who well, let's see. As you age, your perception of light diminishes. So that's why we have difficulty driving at night. As we get older, our cones, the rods, which we use for night vision, gradually fall off in effectiveness. So back to LIGO, we've got these two mirrors. They're 2 kilometers apart. So each arm has 2 mirrors, 44 kilograms. Now, we know how long it takes light to travel from one mirror to the next. So the mirrors bounce light back, and you time that. So as they stand, the mirrors light is bouncing back between the mirrors, and it is at the speed of light. So we know how long this arm is. It's 2 kilometers. We've measured it precisely. We've measured it to the to less than an eighth of the width of a hydrogen atom. That is very small. I believe it's something like 10 to the minus 12 centimeters. Very, very small. Now, light we know is a photon, and we know it's a particle because it has energy. And if you put 2 photons together and they hit something, they hit it with double the energy of 1 photon. So you can actually count photons, right? They're a particle. But they also have the property of a wave. If you have 2 slits in a, you need a coherent source of light, so 1 wavelength. So we use sodium, and you shoot sodium through 2 slits. Behind, you will see black and yellow stripes. That is an interference pattern. So that is called interferometry. So LIGO stands for Large Interferometric Gravitational Observatory. So it's built to see gravity waves. There are a number of people who are important to this, one of which is Kip Thorne. And he gave a lecture a couple of days ago in Princeton, in McConnell, at A02. I posted this on my Facebook page. And he gave a lecture about the LIGO project in much more detail than I'm giving. I gave this presentation on the morning before he gave his presentation. So I'm telling you stuff that I knew before going to his presentation. So I came to his presentation with what I'm telling you now. So we've got the gravitational wave detectors. They are just sitting there waiting for a gravitational wave to come through. Now, you know that the mirrors are suspended, so a tractor running across the surface, is that going to make the mirror bounce? No, it's not. Is an earthquake going to make the mirrors bounce? Yes, it is. Now, an earthquake lasts a certain amount of time, right? So you can, they can tell whether what's happening is an earthquake or a gravity wave. They have very different signatures. They have no problem in this one place, without reference to anybody else, knowing whether what they're seeing is a gravity wave or not. Kip Thorne has spent a long time working on the the computer simulation of large objects coalescing. So what happens when two black holes come together and merge and become one bigger black hole? When that happens, it is theorized, or was theorized, that there was a release of a huge amount of gravitational energy that would be a gravitational wave. This is what LIGO is trying to see. Now, LIGO was turned on for the second time. I'm not going to talk about the first time it was signed on, I'm just talking about the second time. The second time they switch it on, everything is calibrated. They are going for something, they can detect something that is the quarter of the width of a hydrogen atom. And what they're looking for is that we've got 2 kilometers, right? We've got 2 kilometers in each arm. A gravitational wave passes through. One of those arms is going to become slightly shorter for a moment, and the other one is going to become slightly longer for a moment. This is a distortion of space-time. We can detect this distortion of space-time. So the LIGO has observed 3 different occasions where black holes have merged. And LIGO can tell from the wave that it sees what the masses are that are involved. So one of them was 2 black holes of approximately 30 solar masses each. Coming together, they come together, they're attracted gravitationally, they start to circle each other. It becomes faster and faster. At a certain point, a lot of energy is being created. These things are moving around each other at nearly the speed of light, or at least a good fraction of the speed of light. There are gravitational forces between the two. These have tidal effects that you can't really see. The black hole is opaque, we can't see it. Light does not escape a black hole. We do not see them. But they're going faster and faster and faster, then they merge. When they merge, some mass is lost. It's theorized that the mass that is lost is converted into gravitational waves. So you can make an estimate of what the energy released at that point is. In this case, it was the energy equivalent to 3 solar masses going out of existence. That is an incredible amount of energy suddenly released in a gravitational wave. But remember, this wave is traveling across the universe in all directions. So you think of it as a spherical wave. When it passes through Earth, we can tell from the amplitude and the energy level of the wave approximately how far this wave has been traveling, because we know roughly that three masses, solar masses, was used to produce this, and it disappeared immediately, was transformed into gravitational energy. We know how much that is. We can predict how much a wave would show here in terms of energy. So they're able to show that the 230 masses was 1.3 billion light years away. That is outside of our galaxy. That's not inside our galaxy, that's outside of our galaxy. So they know that that the black hole has coalesced. They know this because of all the computer simulations they did of these events. So they knew what to look for. And they found it. They found it 3 times. In fact, Kip Thorne said they'd made 5 observations up to this point. They've also made an observation of 2 neutron stars coming together and rapidly circulating each other until they collide. And it makes a chirp. It goes, that's what it sounds like. just one. It's a chirp, known as a chirp. The signal is very, very distinctive. Cannot possibly be an earthquake. It's not a tractor running by. We know this. We know that is two neutron stars coming together. Things they expect to see in the future are neutron stars being eaten by a black hole. Right? These are theorized that a black hole would have a neutron star in its orbit and would be taking material away from the neutron star. Hydrogen gas would leak from the neutron star as it's orbiting into the black hole. Also, the tidal forces on the neutron star would be big. The neutron star would have a very erratic orbit around the black hole. We can possibly see that with our telescopes that measure other, gamma rays. We're not necessarily going to see this in light, visible light, but we would see gamma rays, and we would see this object with a very erratic orbit. That would tell us, yeah, that's maybe a neutron star around a black hole. This has not been observed yet. They just expect that, to see one of these in the future, and they know what it'll look like because of the computer simulations. Right now, LIGO is currently not operational. They're changing it so that it is 3 times as sensitive. So we've gone from a quarter of a hydrogen atom to divide that by 3. We're now a 1/12 of a hydrogen atom. We can detect a 1/12 of a hydrogen atom difference in the 2 arms. Remember, one is getting compressed, one's getting longer. They're actually oscillating. It's getting one is getting longer and shorter, and the other one is getting longer and shorter. And one's getting shorter when the other's getting longer, and the other one's getting longer when the other's getting shorter. So you've got enough information there when you record what's going on with these things to create a pattern. They know the pattern that they're looking for. When they see it, they know, 2 black holes, 2 neutron stars. So they recognize the neutron star. Remember, it's got the chirp, neutron star. I have no idea what the sound of 2 black holes coalescing is, but it's known. And they also know what the signal will look like when it's a neutron star being swallowed by a black hole. Eventually the neutron star will fall into the black hole, and there will be some huge amount of energy expelled. So mass will be converted into energy, and that will be transformed into gravitational waves, and we will see those gravitational waves. And they expect other phenomena to become visible that we don't, become detectable that we don't know what it is yet. So they expect to have surprises. So what they're saying is this is a brand new way of looking at the heavens. So 400 years ago, Galileo turned the telescope to the heavens and saw moons going around Saturn. And that began astronomy as we know it. The study of the stars, scientific inquiry into the motions of planets, to how the sun works, what stars are. We've made a lot of advances in these 400 years with the telescope, with the optical observatory. We now have a completely new tool to examine other phenomena that are not visible to us, but that produce gravitational waves. And we can increase the sensitivity of this, and we know how to do that. The obstacle to improving the technology is money. What else? So they envisage in the future having 2 arms that are actually 40 kilometers each. Now you might think that there are not many places on Earth where you could have 40 kilometers like this. You know, each arm is 40 kilometers. But apparently there are a number of places that they've spec'd out where they could do this for minimal cost. The real cost comes in the vacuum. You have to have a really good vacuum between these things, because the speed of light that you're measuring is dependent on the photon not hitting anything. So you can only guarantee it's not going to hit something if you have a vacuum. So the vacuum is better than, it approximates the vacuum of space. The vacuum that you would get if you went from here to the moon. Most of the way there's nothing. Most of the way there is something like 5 hydrogen atoms per cubic meter. That's what they need the vacuum to be. Now, a vacuum that's that big, 44 kilometers, is going to cost a hell of a lot of money. So it's not possible for us to do this now because we don't have the money. No government is going to spend this amount of money. The LIGO costs a couple of billion. A couple of billion has been spent on LIGO. There are 2 LIGOs, so you've got a couple of billion spent twice. There's also another thing in Italy known as Virgo, where the G stands for gravity, and who knows what the other things stand for. But those 3 observatories together saw the phenomenon of the 2 neutron stars that collided and sent out a gravity wave. The chirp, bloop, that was detected in 3 different places on Earth. So one site gets the wave before the other. So they get it in 3 different times. Remember, the wave is going at the speed of light. Why is it going at the speed of light? It's because it's a massless particle, and all massless particles go at the speed of light. That's just a physical law. So they know this one, then this one, then this one. So they can tell where in the universe, by triangulation, where this originated. And they did that, and they pointed a terrestrial light sensing telescope in that direction, and they found a large bright object that diminished over time. So like a little bit like a supernova, where it went off, produced a lot of light, but it's not like the sun, which is producing light all the time. It just produced a lot of light, and then the light fades. It's losing its energy. It's at the end of its life. And fades away, and so the 3 observatories together could tell the terrestrial telescope where to look in the heavens. So we know, yeah, that's where the neutron star was. And the LIGO is off. When it comes back on, it's going to be 3 times as sensitive. So guess how many times bigger. If we're looking at a unit sphere, we'll say it's 1. What is the multiple now that we've increased the length 3 times? Is it 3 times as many? No, it's not. Is it 9 times as big? No, it's not. It is 27 times bigger. So instead of 1.3 billion years, we can go out 4 billion years or more. 3 times 1.3, so it's roughly 4. It's a bit more than 4. So 4 billion years we can look back, which is about the age of the Earth. A little young, a little less than the age of the Earth, but you will be able to see 27 times as many events. So we can expect to see in a year 27 neutron star absorptions, and we can see probably 5 times 27 So 270, 130, 135 black hole absorptions. Two black holes coming together making one black hole. So we can expect to see 135 of those a year once it's turned on again. Once we have the 40-foot guys ready, we can expect to see a black hole merger every day, one a day. Okay, thank you for your time. I hope that was useful. Thanks.